Newton's, not Newton's, but laws of motion. That is chapter 4 of class 11 physics. I did the first law and basic introduction in the first video, and the second law, Newton's second law, in the second video. And now today in part 3, I'm going to do, or basically read, the third law of motion, and if possible beyond that. Laws of motion doesn't only consist of laws of motion. So okay, let's start. Laws of motion chapter 4. Third law. We can say the third law is the most famous law of Newton, and every person, at least most of the people know this law. That is Newton's third law of motion. The second law, which is the momentum and force law, which is force equals mass into acceleration or change into momentum per unit time. Change in momentum per unit time is a force. That is the second law, and inertia is the first law, where inertia means the tendency of the body of any mass m to oppose the change in its state of either rest or uniform motion. Now let's see the uniform's law of motion. The second law relates the external force on a body to its acceleration. The second law relates the external force. In the first law, the net force was always zero, and the body used to retain its state of uniform motion or would become rested, would go to the state of rest. And second law, where the external force was not zero, and this external force was related to the body to its acceleration. What is the origin of external force on the body? Okay, there is a question here. They're asking, what is the origin, like where did this external force come from on the body? What agency provides the external force? Which agent or what kind of any kind of thing? Just a minute. Okay, let's continue. The Newton's third law of motion. The second law relates to external force on a body to its acceleration. What is the origin of the external force on the body? Okay, what agency provides this external force? The simple answer in the Newtonian mechanics is that the external force on a body always arises due to some other body. They're defining that any kind of external force on a body, we before and all we did not discuss what kind of like how the force originates. We know that a body is experiencing force and this force is provided by a external agent. We didn't know the external agent, but they are providing the external agent here. The external agent is nothing but the external force on the body always arises. This force arises due to some other body. That is in case of Newtonian mechanics. The force is always due to some other body. Now consider a pair of bodies A and B. B gives rise to an external force on A. Okay, there are two bodies. Let's open up Word here. Now the chapter is laws of motion. Laws of motion of physics. They're taking a body of mass A, and that was not a good circle. Okay, let's take it as A. Let's take it as B. A pair of bodies A and B. B gives rise to an external force on A. B is giving rise to an external force on A. A natural question is, does A in turn give rise to an external force on B? Basically, if there are two bodies here, A is giving a force on B. Let's assume it is two balls are hard to imagine. So let's assume it's a hand. It's a hand pushing something like a ball or any kind of block or something like that. When that happens, when we are pushing something, then does that mean only the block that we are pushing is experiencing a force, or our hands or us in a whole, we are also experiencing a force? Is that possible? That is the question they are asking here. When we are pushing something, is the block we are pushing the only one that is experiencing the force, or even our hands are experiencing a force? In some examples, the answer seems clear. Here, in some examples, like in reality, some kind of situation we will know the answer, but not all we cannot relate to the same thing. But they are giving an examples where it can seem clear. If you press a coiled spring, okay, a coiled spring is basically nothing but the spring. The spring is compressed by the force of your hand. When you are compressing the spring through the force of your hand, the compressed spring in turn exerts a force on your hand and you can feel it. But what if the bodies are not in contact? Basically, the first example is when you are compressing a spring. When you are compressing a spring, of course you can you can experience that the spring is also pushing on you. The spring is resisting the change. It's basically the force is also experienced also on your hand, also on the spring. But in this case, we are in contact. But what if the bodies are not in contact? Then also if, for example, gravity, Earth is exerting force on the moon through gravitational force. It's exerting gravitational force on the moon. Then does that mean Earth is also experiencing force due to the force that is Earth is providing for the moon? Let's read, we'll understand more. The Earth pulls a stone downwards due to gravity. Okay. Does the stone exert a force on the Earth? In the coiled spring case, we easily understood that The spring is of course putting a force on our hands, but what if in this case, when the earth is pulling a stone downwards due to gravity, does the stone also exert a force on the massive earth? The answer is not really obvious since we hardly see the effect of the stone on the earth. It is extremely negligible. And the answer is whether the stone exert a force on the earth. The answer is, according to Newton, is yes. The stone also exerts an equal and opposite force on the earth. We do not notice it since the earth is very massive and the effect of a small force on its motion is negligible. Basically, let's assume the earth is pulling a stone downward with a 10 Newton force when the stone is 1 kg. This 10 Newton force can obviously pull the stone down. But what if we know that the stone will also exert a 10 Newton force on the earth? But do you think for a mere 10 newtons, which is very less amount of force, the earth will move upwards? Of course, obviously not, because the force is extremely small compared to the mass of the earth. Thus, according to Newtonian mechanics, force never occurs singly in nature. Basically, a force is never single, it will always be double, like in pairs or more kind of forces acting towards each other. Force is the mutual interaction between two bodies. Force is a mutual interaction, a point to be remembered here. According to Newton mechanics here, force is never occurring single in nature or due to a single body or so. It is due to a mutual interaction between two or more bodies. Forces always occur in pairs. This is also a point to be remembered. Further, the mutual forces between two bodies are always equal and opposite. The mutual forces between two bodies is always opposite and equal. This idea was expressed by Newton in the form of third law of motion. Let's read this paragraph, which seems to be important. According to Newtonian mechanics, forces are never occurring singly in nature. Force is a mutual interaction between two or more bodies, or basically only two bodies here. Forces always occur in pairs, okay? And for further, we can say force is a interaction between two bodies, and mutual forces between two bodies are always equal and opposite. This is the idea expressed by Newton in the form of third law of motion. This is a statement here, the very famous statement of the Newton's third law of motion. To every action, there is always an equal and opposite reaction. Newton's wording of the third law is so crisp and beautiful that it has become a part of common language. That is what I mean here. Popular, famous. To every action, there is always an equal and opposite reaction. For the same reason, perhaps, misconceptions about the third law started. Basically, there are some misunderstandings of the third law that we will see. Let us note some important point about the third law, particularly in regard to the usage of the terms action and reaction. The terms action and reaction in the third law means nothing else but force. Using different terms for physical concept can sometimes be confusing. A simple and clear way of stating the third law is as follows. Basically, when in terms of usage of action and reaction, like action and reaction is basically nothing but the force only. We are talking about force, so of course it's about force only. The action is also through the force, the reaction is also through the force only. Basically, they're giving a simple statement here. Forces always occur in pairs. Force on a body A by body B is equal and opposite to the force on body B by A. Basically, let's read the statement again. Force on a body A. A body A is there. That instead of force on body A and body B, we can say our hands and a block. When we push a block, the force we apply, this is my question from before actually. When we push a block with our hands, we apply force on the block, and the same way the block will also apply a force on us. If we see this, if we observe this, if we try to understand this more clearly, basically I'll write the statement here. If we apply force on a block, then the block or a car, a trolley, whatever, will also apply equal and opposite force on us and our hands. Points. Okay. Let's examine the statement further. This is what basically a body A, body B. This is exactly what we are saying here. The forces always occur in pairs. Force on a body A by B is equal and opposite to the force on body B by A. This is an example of that statement here. This is the physical representation here, a block, and it is like a lotus, but it is a hand. When we push this block, our hand will also, there is a force that the block will apply on our hand. If we see this, it is similar to the normal reaction forces, like when on, let's assume there is a ground here, and let's assume there is a block here. The earth is applying a force, like basically the earth is pulling this block downwards. This is actually same as like when we are pushing the block, and when earth is applying a downward force like this is the same as pushing one as well. This is the same as the pushing force, or earth is pulling it towards the earth. In this case, we see normal force. We see the earth is also applying equal and opposite normal forces here. The earth is pulling the block downwards to gravity and is also applying normal force here. This is easier to understand than this pushing a block scenario. This both is basically the same thing actually. When the block is applying a force due to gravity on the earth, the surface here, or a table surface, is also applying an equal and opposite force of the gravitational force upward. That is called the normal force. In this case, force in gravity is equal to this magnitude here, force in Newton, and not Newton, but normal forces. Why this happens is because why we assume there is a force that is acting upwards, that is a normal force, is because if earth is pulling the block downwards, we obviously know when something is acting downwards, it should, when there is a force acting on something, it should feel an acceleration. So why wouldn't the block go accelerate towards the center of the earth? We know that because the earth's surface or the table surface, whatever it might be, is pushing the block upwards. That is what we assume, because we know that the block is not rushing downwards. It's not going to the center of the earth. Something is blocking that force. It's opposing that force. That is called as the normal force. In here as well, when we are pushing the block, if the block is not giving an equal and opposite force, wouldn't our hand go directly through the block? Like, wouldn't the hand directly go through the block, like if there is no opposition only? if the block is not applying a force on our hand, like how the block here should directly go toward the center of the earth, this hand also should go directly through the block as it is like an ethereal block or something like that. That is not the case. We do not, our hand does not pass through the block. That means when we are applying a force on the block, we are not going, our hand is not directly going through the block. That means something is opposing our hand from going into the block. That is basically the reaction force. Our hand is pushing the block, that is action, and the block is also applying a reaction force, that is a reaction. If there was no reaction, our hand would have directly gone through the block as if it was air. Understanding this simple thing gave us the third law of Newton, or third law of motion basically. Oops, I forgot to add more pages. The terms action and reaction in the third law may give a wrong impression that the action comes before the reaction. That is, action is the cause and reaction is the effect. There is also a misconception here, which is that the action and reaction pairs like do not happen at the same time. There is a misconception here. Like when we do an action, then the reaction comes. This action is misconception here. That is not the case. There is no cause and effect, meaning there is no after and before. Action comes at the same instant. A reaction also happens. There is no cause effect relation implied in the third law. That is what it means. Basically, both happen at the same time. The force on A by B and the force on B by A act at the same instinct. Not instinct, but instant. By the same reasoning, any one of them may be called action and the other reaction. Okay. There is no cause effect. Let's read the statement. Let's read the statement again. There is no cause effect relation implied in the third law. The force on A by B and the force on B by A, where B and A are two different bodies, are acting at the same instant. By the same reasoning, same statement here, any one of them may be called either the action, either the force on B due to A is called as, we can call it as an action, or the force due to A on B also we can call it as a action, or we can call either of them as reaction. There is no difference. Action, the third point we are saying here, action and reaction forces act on two different bodies or many different bodies, not the same body. Consider a pair of bodies A and B. According to the third law, force on A by B is equal and opposite to the force on B by A. And a very important point to be remembered here, action and reaction forces occur on two different bodies. It never occurs on a single body. We do not consider a single system of a body and make it as an action reaction pair. That is never the case. When the ball hits a wall, when we throw a tennis ball or a cricket ball at the wall or any kind of fence or whatever it might be, the action reaction pair is not the ball, but the ball as well as the wall. Both are considered as the two bodies here. Thus, if we are considering the motion of any one body, A or B, only one of the two forces is relevant. Okay, it is an error to add up the two forces and claim that the net force is 0. Basically, because we know that the force on two bodies is equal and opposite, we only need to consider the motion of one of the particles. Only one of the, not particles, but only one of the two forces is actually useful because they are equal and opposite forces. Only one of them is considered. Actually, it's relevant. But we cannot say just because, like, we cannot say because it's an equal and opposite force, the net force, we can't say it is a zero force. That is wrong. We cannot say this minus and plus will add up to become a zero and the net force will become zero. That is an error. However, if you are considering the system of two bodies as a whole, that is FAB and FBA are internal forces of the system A plus B, they add up to give a null force. Basically, in case of two different systems, when we consider two different bodies, like, yes, two different bodies, A and B, the hands and a block, then the adding up the whole force of our hands and the system, not system but the block, to be zero. That is wrong when we consider two different systems. But let's assume when we consider only one system. But you might be confused as to say, we know that the force is acting on two different bodies. It is never a single system. So how can we consider a single system? In a single system, we do not consider the force on the system, but the internal forces of the system. Basically, in a system, if we consider a system of a part of air, basically we consider, we take a glass chamber. In that chamber, there are air particles. That is one system of ours. And in this system, where the entire force, internal forces of the system, that will become, that we can say it is zero. But we cannot say that the force on the system, entire system, is zero. Here inside the system, there are many particles. Here it will always be in pairs. So it is following the Newton's third law. But when we are considering the whole system, it is only a single system. So we cannot consider the force on a system to be in accordance to the Newton's law. In a single system, we cannot consider the single system to be following the third law. Internal forces in a body or a system of particles thus cancel away in pairs. This is an important fact that enables the second law to be applicable to a body or a system of particles, which we are going to see in chapter 6 of 11th standard textbook of course. Let's read the statement again. Internal forces in a body or a system of particles cancel away in pairs. This is an important fact that enables the second law to be used to a body or a system of particles. Now let's see here. Two identical billiard balls strike a rigid wall with the same speed but at different angles and get reflected without any change in speed. Okay, here two identical balls strike a wall with the same speed, initial velocity is same, but at different kinds of angles, and get reflected or deflected without any change in speed. The speed remains constant as shown in figure 4.6. Basically this figure here, this is the first ball where it is bouncing back in the same path. This is the same path, but in the second case here, the ball comes like this, and it is making a 30-degree angle with the vertical here. This is the vertical, this is the horizontal. This is the vertical and this is the horizontal. And it is making a 30-degree angle with the vertical here. And in the same way, it is again making a 30-degree angle here and getting reflected like this. But the velocity remains same. The direction of the velocity changes, but the velocity remains same. Here as well, in the first case as well, the direction of the velocity changes. It is exactly opposite here. The first is coming this side, now it is going this side. two identical billiard balls strike a rigid wall with the same initial velocity but at different angles, and they get reflected without any change in speed. In the first question, the direction of the force on the wall due to each ball is. They're asking the direction of the force on the wall due to each ball. Okay, they're asking the force that the ball applies on the wall. The ratio of the magnitudes of impulse imparted to the balls by the wall. Okay, they're asking here two things here. They're asking one, they're asking here are the force, the direction of force imparted on the wall, which we can see here. The force imparted on the wall by the first ball, it is directly like this. It is perpendicular, it is normal to the horizontal wall. Like this, it's into the wall, the force. And in this case, it is like this, where the first force where the force is in this direction, and it can be deflected, it can be changed into two different components of this component and this component, where the wall will apply an exact opposite of those, which is in this direction. The force will be in this direction. Okay, then let's read what the answer they give. The first thing is the direction of force, and an instinctive answer to first might be that the force on the wall in case of A is normal to the wall, while that in case of B is inclined at 30 degrees to the normal. Wait, they are saying this is wrong. So whatever I said might be wrong. Let's see. An instinctive answer to one might be that the force on the wall in case of A is normal to the wall, while in case of B is inclined at 30 degrees. The force on the wall is normal to the wall in both cases. Okay, what I said is indeed correct. Yes, it is indeed correct. Here as well, the force is normal to the wall. In this case, it is normal to the wall. In this case also, this component doesn't matter here. This component is not acting on the wall, so this doesn't matter. So when we resolve it, only this component matter. So then it is also normal here. How to find the force on the wall? The trick is to consider the force or impulse on the ball due to the wall using the second law, and then use the third law to answer it. Okay, they're saying first we need to do is how to calculate the force on the wall is the first we need to do is consider the impulse on the ball, and through the second law, and then use the third law to answer it. Let u be the speed of each ball before and after collision with wall, and m the mass of each ball. Choose the x and y axis and show the figure, and consider the change in momentum of the ball in each case. In the first figure, where it is completely like this, here case A, momentum on the x direction initial, which is equals to m times u. The y initial is 0 because there is no velocity acting in that direction. The velocity only acts in this direction. There is no action in the y direction when we resolve it into y and x components. So p of y will be 0, and p of x final will be negative mu using direction here, and p of y will always remain 0. Impulse is a change in momentum vector. Impulse is a change in momentum vector. Therefore, x component of impulse, which is equal to minus 2 mu. Basically, impulse, it is basically, we can define impulse as the change in momentum. So the change in momentum, the initial momentum, final momentum minus initial momentum. Final is minus mu and initial is mu. So the change in momentum is minus mu minus of plus mu, which is basically minus 2 mass times initial velocity. Not initial velocity, just velocity, or we can say speed. But since they are considered actually minus here, we need to call it actually velocity. Y component of the impulse will remain 0 here in the first case. Impulse and force are in the same direction. Force also, we know this is actually a point from before in the second law we read that says that impulse and force are always in the same direction. Clearly from above, the force on the ball due to the wall is normal to the wall along the negative x direction. Let's read that statement again. Impulse and force acting in the same direction, and from that statement, the force on the ball due to the wall is normal to the wall. Okay, along the negative x direction. This is the force one. Basically, they are saying that what that statement means here is, let's open. When we take a wall here, and in case of a ball which is going normally like this, normal direction, and like this, where the initial velocity will remain same, this is the case they are talking about. And I think what they said, this is the force on the ball. In this case, the force on the ball here at this position, the force enlarged view, okay, here the force on the ball is in this direction. The force is acting in this direction. And in case of the wall, the force, this is the force on the ball due to the wall, which is acting when we resolve it into the axis or the coordinates. It is positive x, negative x, y, and negative y. When the force on the ball due to the wall is acting in the negative x direction, and in case of the force on the wall due to the ball, which is acting in this direction, force on the wall due to the ball is acting in this direction. In this case, it is positive x direction. Here, the force on the ball is acting in the negative x direction. That is the reason when the ball collides with the ball, and not the ball collides with the wall will bounce back, and instead of going through the wall, because the wall is applying a force in the opposite direction, in the exact opposite direction, negative x-axis. That is the reason, instead of ball going like this, or any other ways, it is going exactly straight in the exact x-axis, in the negative x-axis to be more specific. Now that is the first scenario. That is what they gave in the statement here. Now, we calculated the force on the wall due to the wall is acting in the negative x-axis direction, and the force on the ball, no wait, not the ball, on the wall due to the ball is in the positive x direction. Now, using the Newton's third law of motion, the force on the wall due to the ball is normal to the wall along the positive x direction. Okay, this is using the Newton's third law, not first. The magnitude of force cannot be ascertained since the small time taken for the collision has not been specified in the problem. We do not know how much force is acting since they did not provide how much time is given here, how much time it took for the ball to collide. They did not given you the velocity here. Velocity, they just gave a constant, not a constant, but a variable. Here we found out the direction, which is normal to the wall, and in a negative x direction for the ball. Case B here, that is for the second diagram where it is inclined, Px total is mu cos theta, which is cos 30 degree along the vertical here, and Py is minus u sine theta initial, because it's acting in the minus y direction, acting downwards here. When we resolve it, we got it to be in this direction. That is why they took minus here. And Px final in the x direction is minus mu cos theta, and Py final, it is minus mu sin theta. Note, while Px changes sign after collision, Py does not change. Therefore, x component impulse is minus 2 mu cos theta and y component impulse is 0. Basically, the change impulse is the change in momentum, and they gave in case of the inclined plane here, not inclined plane, but the inclined collision here at the second case. The ball is making a 30-degree angle like this. The velocity does not change here, and when we resolve the velocity in the x and y axis, x dash, y and y dash, this is the velocity component. Let's take it as u only. This can resolve into u cos theta in the horizontal, and actually this is not u cos theta, u 30 degree actually, u 30 degree, because they voided the angle here, and u sine 30 degree. This is the resolution of the u vector. When we resolve this vector, we will get this direction, and we know that impulse equals change in momentum. T is the representation of momentum, so delta impulse equals P final minus P initial, and in case of the x and y axis, it is impulse equals impulse in the x direction equals Pfx. It's not a function actually, so momentum, we know momentum equals mass into velocity, so mass into, in the x direction it is, x direction in this case it is u cos theta, m u x cos theta, cos 30 degree, this is in the x direction, and impulse minus wait, this is actually the final impulse is minus, the initial impulse will be mu x cos theta, and when we do the signs here, impulse in the x direction equals to minus 2 mu x cos 30 degree, and in the y direction, if you want to calculate impulse in the y direction equals change in momentum, which is equals to P final minus P initial, and this is equal to, and here it is minus u sine theta, minus not u sine theta but minus mu sine theta, minus of minus mu sine theta, let's keep it theta itself, minus mu sine theta plus mu sine theta. That seems like a motion, but it is mu sine theta. So impulse in the y direction equals 0. How we know that the there is a minus here, there is a minus here, or a minus here, or in case of this one, why there is a minus here and there is a plus here? How we know that is based on the coordinates here. In this direction, when we resolve the vector in the x direction, this is positive because it is acting in the plus x direction. If we see, it is acting this way, so it is in the plus x coordinate. But this one, it is acting downwards, which is basically y dash, so it is negative. That is the reason. But in case of this case, when we resolve, this is the initial vector, and in case when we resolve the second vector after reflection, this is the vector, and in this case as well, it is resolved into two vectors of minus u cos theta and minus u sine theta. In this case, it is minus u cos theta and minus u sine theta is because in this case the resolution of the u vector in the left direction, which is the x dash direction, so it is a negative here, which because it's acting in the negative x coordinates. And in case of this one, not this one, it's in this direction. This is the same as the initial case where both cases the velocity is acting downward itself. So in such a case, this will remain as minus u sine theta. And based on these values, I substituted in the impulse, which is equals to change in momentum. This is the main equation. This is from the second law of motion. And based on this, the impulse on the x direction is minus 2u. We can write ux here, or normal u is enough. It is normal velocity. Since we wrote cos 30 degree here, there is no need to write ux there. Minus 2 mu cos theta, or cos 30 degree, which is basically cos 30 is root 3 by 2. So impulse in the x direction equals minus 2 mu cos 30, and I think it is root 3 by 2. So it is impulse equals minus mu root 3. That's a parallelogram. Anyways, the x component impulse is minus 2 mu cos 30 degree, and y component the impulse is 0 degree. The direction of impulse and forces is the same, and in A, that is the first diagram here, it is normal to the wall along the negative x direction. As before, using Newton's third law, the force on the wall due to the ball is normal to the wall along the positive x direction, normal to the wall. The ratios of magnitudes of the impulse imparted on the ball. In case of the first case here the impulse came to be around cos 0 equals 1, so minus 2 mu. So okay, minus 2 mu here. So when we divide minus 2 mu by minus 2 mu cos 30 degree, it will be 2 by root 3. It is approximately 1.2 is the ratio. And this paragraph here means that this is basically the direction of the impulse, and the force is same. That is a point here to be remembered. The direction of the impulse and the force is same in direction. Using Newton's third law, the force on the wall due to the ball is normal to the wall. Basically, they're saying the force is in this direction. It is normal to the wall. That is what they're saying. That's all. And the ratio is 1.2. That's the sum here. Now let's go to the next main topic here after the third law, that is conservation of momentum. The second and third laws of motion lead to an important consequence, the law of conservation of momentum. Conservation of momentum. Basically, this is also better to be remembered that The second and the third laws of motion lead to an important consequence. A consequence of the second, we can, another way to word this or say this statement consequence of the second and third laws is the theory or the law of conservation of momentum. Not theory, but it is a law. The consequence of the second and third laws is the law of conservation of momentum. Take a familiar example. Okay, they're saying an example here. A bullet is fired from a gun. Okay, if the force on the bullet by the gun is F, the force on the gun by the bullet is minus F according to the third law. The two forces act for a common interval of time, delta T. Basically, they are taking a firing a gun. When we fire a gun, there will be recoil. There will be recoil due to why this recoil happens is because the force the gun is exerting on the bullet, the same force the gun will also experience, and the person who is holding the gun, basically the person who is holding the gun, will also experience the same force. The forces okay, according to the third law, the force on the bullet and the force on the gun act at a common interval of time, delta t. They're acting at the same time. This is also important to remember. They're acting at the same interval of time. Not in this case, not in this case only, but generally as well. According to the second law, F times delta t is the change in momentum of the bullet, and minus F times delta t is the change in momentum of the gun. Okay, where it is the change in momentum is same but opposite. Since initially both are at rest, initially before firing a gun, the bullet is also loaded in the gun and it's in rest state. The gun is also not moving. The change in momentum equals the final momentum for each. Basically, the change in momentum equals the final momentum for each. Thus, if PB is the basically momentum of bullet is the momentum of the bullet after firing, and PG is the recoil momentum of the gun, PG equals minus PB, where PG is the momentum of the gun, which is equal and opposite of the momentum of the bullet, where if we add the momentum of the gun and the momentum of the bullet, it will be equal to 0. This is the total momentum of the bullet. System is conserved. Okay. This is just a statement here that says that the change in momentum for the gun and the bullet will remain equal and opposite. And through that, when we add the total momentum before firing the gun and after firing the gun will remain equal. Thus, and this is in case of in a isolated system with a system with no external force, mutual forces between pairs of particles in the system can cause momentum change in individual particles. Mutual forces between pairs of particles in the system can cause momentum changes in individual particles. In an isolated system where the system is not experiencing any external forces, mutual forces between pairs of particles that is inside the system can cause momentum change that is inside the system. But inside the system, there is a momentum change also. The whole system momentum is conserved. But since the mutual forces of each pairs are equal and opposite, the momentum changes cancels in pairs and the total momentum remains unchanged. The fact that the total momentum for a system will remain conserved is known as the law of conservation of momentum. The total momentum of an isolated system of interacting particles is conserved. An important example of the application of the law of conservation of momentum is the collision of two bodies. The more important example or application of this law of conservation of momentum, where this law of conservation can be momentum can be applied, is the collision of is during a collision of two bodies or two particles. Consider two bodies A and B with initial momenta PA and PB. The bodies collide, get apart with the final momenta P-A and P-B respectively. And by the second law, force on A due to B times delta T, the time interval, which is equals to PA dash minus PA, and force on B due to A times delta T is equals to delta B, not delta, but P dash B minus P dash PB. This is basically on the second law, the momentum change of the bodies. Why we take momentum of A and momentum of B separately when the force is experienced on A is because we know that the momentum change in case of force, when we calculating the force on a body, on a single body, we are calculating the force on that body. Then why we take individual momentums here, PA or P dash here, and not PA minus PB here, is because when calculating the force of a body, we consider the change in momentum of that particular body. When we are considering the force on a single body, we consider the momentum, the change in momentum of that body only. So in such a case, when we consider PB here, it will be not the change of the momentum of that body. We are including something else there. So when we are finding the force on A, we only include PA on, like the change in momentum of the A only, the A body only. When we are calculating the force on B, we include only the force or change in momentum of the B body only. This is according to the second law, where we have taken the common interval of time for both forces, that is the time for which the two bodies are in contact. Because we are taking two bodies here, the time for which they are in contact will of course remain common. And according to our Newton's third law, F force on A due to B, and which is equal and opposite to the force on B due to A by the third law. And we know that since the time intervals are common, we can write it as the change in momentum of A, which is equals to the negative of the change in momentum of B. So this is actually a derivation for the conservation of momentum. That seems to be the case. Basically, from the third law and the second laws, we can write the initial final total sum of the final momentas of the both bodies, which is equal to the sum of the initial momentum of the bodies. The sum of the final momentas of the two bodies is equal to the sum of the initial momentas of the bodies. And that is what they're saying, which shows that the final momentum of the isolated system equals its initial momentum. Notice that this is true whether the collision is elastic or inelastic. Basically, this conservation of momentum will always be true even if the collision is elastic or inelastic collision. What is elastic and inelastic collisions? We will see. In elastic collisions, there is a second condition, that the total kinetic energy, initial kinetic energy of the system equals the total final kinetic energy of the system. Basically, in elastic collisions, we will see that the total initial kinetic energy of a system, this initial kinetic energy before collision, which is equal to the total final kinetic energy after collision. Equilibrium under concurrent forces. Okay, this is a diagram showing three different representations here. This is the force F1 and F2. When F1 and F2 are in constant, not constant, I mean equal and opposite, the system will be, when F1 and F2 are forces acting on a system, and F1 equals in magnitude, F1 and F2 are equal, and in terms of vector forms, F1 is equal and opposite to of that of F2, and these forces are acting on a body, then the body will be in equilibrium. And in case of the second diagram here, the force 3 is resoluted into two different forces, the F1 and F2. In the third diagram, the F2 and F1 forces, right? This is a concurrent force, right? Okay, fine. In other words, what? Wait, wait. Okay, I missed the equilibrium of a particle here. Sorry for that. Basically, energy of the system. This is in case of elastic collisions, where I was before that I was talking about elastic collisions here written here. In elastic collision, there is a second condition that the total initial kinetic energy of the system equals the total final kinetic energy of the system. This is in case of elastic collisions and elastic collisions only. We will read more about this in the next chapter, which is the work, energy, and power. Now let's go to the next main topic. But before that, I will be taking a 5-minute break. Hang around, and you also take a break. It seems the break took a little more than 5 minutes, but okay, let's continue anyways. Now let's go to the topic, next main topic, that is equilibrium of a particle. Equilibrium of a particle in mechanics refers to the situation when the net external force on the particle is zero. It's a point to be extremely important to be remembered, that is, the equilibrium of a particle in mechanics refers to the situation when the net external force on a specific system or a particle is zero. Another way of saying that is, when the net external force acting on a system or a particle is zero, then we can say that that system or a particle is in equilibrium. According to the first law, this means that the particle is either at rest or in uniform motion. According to the first law, the law of inertia, or basically something similar to that, that is basically when the net external force on the body is zero, then that means the particle is either at rest or in uniform motion. Then if two forces F1 and F2 act on the particle, equilibrium requires F1 equals minus of F2. If two forces, there is in the real world, it is very hard to create a scenario where actually the net force on the body is zero. So in such a case, we can take where the net force on the body should be zero. The actual force, there will always be a force acting on the body. It is almost impossible to create a situation where there is no force acting on a body in the real world. But we can take the net force to be zero, not the force, but the net force acting on the body to be zero. If two forces F1 and F2, let's consider a two-force system where a system is experiencing forces of two different forces, where F1 and F2 act on a particle or a system, and when if we want the equilibrium of that particle, then F1 should be equal and opposite, exactly opposite of F2. That is, the two forces on the forces must be equal and opposite so that they cancel out to give the net force on the body to be zero. Equilibrium under three concurrent forces F1, F2, F3 requires the sum of three forces is to be zero. And this is not talking about, in case of the third law, we saw that we can't add them and we can say that the total force on the body is zero. We cannot say that there. But here it is not two particles that are acting here. We are finding the force on a single body. It's not a pair here. The force that is acting on a single body. This is a misconception here, where the force acting on a single body is different from the action-reaction pairs from the Newton's third law. Okay, let's continue. Here, if two forces on the particle must be equal and opposite, equilibrium under three concurrent forces. This can also be the case, and there can also be three forces, that is F1, F2, and F3. Then if we want equilibrium under that condition, then we need to sum up all these forces vectorially, like vector addition or vector sum. When we get the sum is equal to zero, then only we can say the body is in equilibrium. Equilibrium of a body not only requires not only translational equilibrium, zero net external force, but also rotational equilibrium, no net external torque. Basically, we can only say equilibrium of a body will attain true equilibrium. They are basically here correcting the definition here. It's not actually correcting, but adding something more onto the definition. Equilibrium of a particle in mechanics refers to the situation where the net external force on the particle is zero. They're adding on and saying that it is not only the net external force that should be zero, but also the net external torque. Torque is a rotating force, a rotating motion, that also should be zero. Now let's say the concurrent forces, when it can be in three. In this, the two equal and opposite forces, the body will attain equilibrium. And in this case, it is three, basically three different forces. This is where the system is. In this system, where there are three forces, the first F3 is acting this way, and F1 is acting this way, F2 is acting this way. In this case, when we take the resultant of F1 and F2, where there is a F4, let's call it the resultant. Let's not do that. This is the F resultant. In this case, for the body to be in equilibrium, F3 must be equal to minus of F resultant. Only in that case will the body be in equilibrium. The third case they gave here is basically this is also a equilibrium under concurrent forces 3, when the net force actually is adding up like this, it's actually becoming a cycle. So in this case, where when we do the vector sum, in this case where it's forming a it's forming a triangle or a square or any kind of polygon, in this case when it's forming a closed loop, the force will be 0, the net force will be 0. In other words, the resultant of any two forces, say F1 and F2, obtained by the parallelogram law of forces must be equal and opposite to the third force. That is what I did here. The parallelogram. Basically, I took a resultant here. The three forces in equilibrium can be replaced by the sides of a triangle with vector arrows taken in the same sense. Is basically the same thing, but taken. We can write this in form of, we can write the F3 vector like this. We can take this F2 vector from here to here and F1 vector from here to here. Doesn't this diagram look the same as this one? That is basically what they're saying here. The result can be generalized to any number of forces. This result is true for many, even if we take n number of forces. A particle in equilibrium under the action of forces F1, F2 to Fn, any number of forces, if they can be represented by the sides of a closed n-sided polygon with directed in the same sense. Basically, they're saying what I said here: if any number of forces can form a closed polygon that is in order, where it is the head of the first force is attached to the tail, here as well the head is attached to the tail. I'm talking about the vectors here, the vector tail and heads, where they are interconnected, where the head is always linked to the tail. In such a case, the total force of the body when it's forming a closed polygon, in such a case, the force that we can say the body is in equilibrium. And we can also say if the total force, if the sum of the vector sum of all the forces acting on a single particle or a body is equal to 0, then the net force on the body is also equal to, not net force, I'm talking about the body will be in equilibrium. Equation 4.11, which is basically here F1 plus F2 plus F3 equals 0, implies that F1x plus F2x plus F3x is the force in the x direction, the y direction, and the z direction. All should be, if vector sum is done, it should be equal to 0, where F1x, F1yx, and F1zx are the components of F1, force F1 along x, y, and z directions respectively. See figure 4.8, this is the figure here. It seems to be more, I need to yeah, this should be, let's see the question. A mass of 6 kg is suspended by a rope of length 2 meter from the ceiling. A force 50 Newton in the horizontal direction is applied at the middle point of the rope as shown. What is the angle a rope makes with the vertical in the equilibrium? Take G equals 10 power 10 meter per second square and neglect the mass of the rope. Basically, mass of the rope is 0. It's not really possible, but ideal situations. This is the first figure here. They took a weight of 60 degree. Mass of 6 kg. So when we take mass of 6 kg, the force acting downwards is of course 60 Newton. And here they took tensions on the rope as well. And here there is a force acting in this direction, that is 50 Newtons here. Okay, and here as well. Okay, this is the individual components of the tensions and the force. Here the body is here suspended like this. A downward force due to gravity 60 Newton is equal to the tension above, which is T2, equal and opposite. And here in the second case, this tension 2 should be equal to the tension 1 and the 50 Newton force here when we do vector sum. Okay, let's see how to do that sum. Actually, if we observe this more carefully, we can divide this into two sections that they are given individually here, where here it is when we draw the free body diagram, the main tension here, from based on this we can say 60 equals T2, which is in magnitude wise only. 60 is a constant, but in newtons, in force, if we take force, this force is equal to T tension 2, the tension, and in this case tension 2 should be equal to the vector sum of these two forces here. So we can equate T2 to be equal to T1 plus 50 Newton vectorially. But since, okay, let's see. Figures 4.8b and 4.8c are known as the free body diagrams. Figure 4.8b is the free body diagram of W and basically the weight, and figure 4.8c is the free body diagram of point P. Okay. Consider the equilibrium of the weight W. Clearly, T2 equals 6 into 10, 60 Newton. That is what I said. Consider the equilibrium of point P under the action of three forces: the tension 1, tension 2, and the horizontal force 50 Newton. The horizontal and vertical components of the resultant force must vanish separately. Basically, T1 cos theta. T1 cos theta is the force in the horizontal direction here. Basically, okay, let's observe the diagram more clearly here. In the second diagram, which is the most important here, erase the marks here. We know that T1 equals T2 equals 60 Newton. Now, these force for this for the block to be, for this point to be in equilibrium, point P to be in equilibrium, the sum of, I think they gave what is the angle rope making? Okay, they gave it as an equilibrium. So we can say the vector sums of T1 plus T2 plus the force, this one force F horizontal, we will take it as FH, should be 0. This is the clue we got. And we should take horizontal components and vertical components separately. If we see T2 and force horizontal, which is a 50 Newton, they do not need to be resolved as they are acting in the horizontal and vertical directions respectively. So the only thing that needs to be resolved is a T1, which is making a theta with the vertical. This T1 should be resolved in the this way. Wait, not this way. This is the force acting like this. This is the sine component, cos component, and this is the sine component. This is T1. This is T1 sine theta, and this is T1 cos theta. This is the resolution. Now, if we want to add up, we need to take vertical components and horizontal components separately. Now let's see how they solved it here. 200% zoom seems to be better here. Okay, T1 cos theta equals T2, which is 60 Newton. When we resolve it like this, obviously the only force acting upward, uh, like which is supporting the T2, which is basically T1 cos theta, which is, wait, T1 cos theta. Okay, wait, I think they took this this as cos theta and this as sin theta. Okay, that this is the angle is with the vertical, so of course they should take like that. Okay, I did the mistake there. In this case, this will be the cos theta and this will be the sin theta, and this is the force, downward force. This is T2. So since the, and this is the basically the free body diagram, 15 Newton, and this is equal to 60 Newton. 60 Newton and 50 Newton here. So there's a free body diagram here. So from this free body diagram, if the body is in equilibrium, I will rub the T1 component here. Actually, I think for the angle, we need the T1 component. So I'll keep it like this. For the angle, this is its angle, making the horizontal angle. Okay, fine. From this free body diagram, we can see that when, if this body, the body here is in equilibrium, we can obviously see that T1 cos theta equals 60, whereas T1 sin theta equals 50 Newton. That is the only reason. When they are equal in magnitude, that is the only reason, and they are opposite, we know. And if only if they are equal in magnitude, this force can be in equilibrium. Not force, this particle in that point can be in equilibrium. So that we can see here, T1 cos theta equals T2, which is equal to 60 Newton, and T1 sin theta, which is equals to 50 Newton. That is what I wrote here. Yes, T1 cos theta equals 60, T1 sin theta is 50, and which gives that tan theta, which is 5 by 6, or theta equals tan 5 by 6, which we know the angle is 40 degree. Basically, they divided this. We know that T1 cos theta equals, I think it was 60. T1 cos theta equals 60, and T2 cos sin theta, wait, not T2, but T1 sin theta equals 50. Now when we divide them, equation 2 and 1, let's take how they took it. So let's divide equation 1 by, equation 2 by equation 1. So we'll get T1 sin theta by T1 cos theta, which is same as 50 by 60. 0, 0 cancel. T1, T1 cancel. We know that sin theta by cos theta equals tan theta. Tan theta equals 5 by 6. And tan inverse of 5 by 6, the angle should be theta, and which is a fixed value, this tan inverse of 5 by 6, which is 40 degree approximately. This is not what we found out, but it is basically a fixed value. That is how they got theta equals 40 degree. Okay. And basically from this we can say the answer does not depend on the length of the rope, which is assumed to be massless. If it was mass, if the rope had a mass, it would have influenced. But if it doesn't have a mass, it will be independent no matter how many kilometers the length of the the string or the rope is. If it is massless, it doesn't matter. nor on the point at which the horizontal force is applied. No matter which point the horizontal force is applied also, it doesn't matter. Now let's go to the next main topic, that is common forces in mechanics. Here in mechanics, we encounter several kinds of forces. In mechanics, we encounter several kinds of forces. For example, the gravitational force, and the gravitational force, of course, pervasive. Every object on Earth experiences the force of gravity. Due to the Earth, gravity also governs the motion of celestial bodies. Celestial bodies is nothing but the planets here, or the galaxies, the stars, many kinds of objects that roam around in the space and which are massive are called as basically celestial bodies. The gravitational force can act at a distance without the need of any intervening medium. Let's read the statement again. In mechanics, we encounter several kinds of forces. The gravitational force is pervasive. Every object on, what does that pervasive and gravitational force is, means that every object on Earth experiences the force of gravity due to the Earth. That's what that means. Gravity also governs the motion of celestial bodies. The gravitational force acts at a distance without the need of any intervening medium. There is no need for medium, be it air, be it water, be it vacuum. The gravitational force doesn't require anything. All the other forces common in mechanics are contact forces. We are not considering, for simplicity, charged and magnetic bodies. For these, besides gravity, there are electrical and magnetic non-contact forces. For normal bodies, where we do not consider magnetic and electric forces, which we are going to study in detail in the 12th standard, and I do have videos about them too. And in this common forces in mechanics, except gravitational force, we consider contact forces. And contact forces is basically contact between two bodies, force due to the contact of two bodies. But in this case as well, we do not consider electrical and magnetic forces to be applied. Only in that case we are considering here. As the name suggests, a contact force on a body arises due to contact with some other object. It may be a solid, a fluid, a gas, or whatever it may be. When bodies are in contact, a book resting on a table, a system of rigid body connected by rods, hinges, and other types of support, there are mutual contact forces for each pair of bodies, satisfying the third law. Basically, let's read the statement again. A contact force on an object arises due to the contact with some other object, solid or fluid. When bodies are in contact, that the above statement is clear. Then when the bodies are in contact, when the bodies are touching each other, the two blocks or anything it might be, when the bodies are in contact, there are mutual contact forces satisfying the third law. That is only for pair of bodies. This table example they gave here. Table, if we take, table is supported by four hinges, four legs, and these legs are supported by hinges, supports, basically supporting the whole structure of the table. This is basically contact forces. The component of contact force normal to the surface in contact is called as normal reaction. Now let's read that again. The component of contact force that is normal to the surfaces in contact is called as normal reaction. When we take surface forces or contact forces, this is applying a force, let's assume the force normal like this, where it's making an angle with the surface enlarged view, where it's making an angle like this, 90-degree here, then this force is called as normal force, normal reaction force, or normal reaction. The component parallel to the surfaces in contact is called friction. The component, that is the component of the contact force, that is parallel to the surfaces in contact, is called as the friction force. Let's try to understand that again. The component of the force that is acting parallel to the surfaces of the bodies. Contact meaning contact force is basically, so this is a block, this is a contact force. I mean a normal force. A normal force is like this or like this, and friction force is basically like this. If we take it, this is the surface of a body, then the angle between them, if we take an enlarged view like this, it will be the angle is 0 degree. Theta equals 0. This is called as parallel. Theta equals 90 degree. Theta is an angle here, which is normal. Contact forces arise also when solids are in contact with fluids. Actually, let's see the before statement. Let's observe the diagram more. This is the normal forces acting normal to the surface of the body, where parallel forces acting parallel to the surface of the body. Okay. It might act in this direction here, like this, or any kind of direction. Okay, fine. Okay, contact forces arises also when it's not only in solid. These contact forces arise also when solids are in contact with the fluids. Also when solids are in contact with the fluid. For examples, we take, for a solid immersed in a fluid, there is an upward buoyant force equal to the weight of the fluid displaced. The viscous force, air resistance, etc. are also example of contact forces. Basically, when forces, like they gave a statement that a solid also experienced a force with liquid, due to liquid also. How is in case of buoyancy, which is basically the force experienced by the object immersed in a liquid, which is equal to the weight of the liquid displaced. And this is also, and they actually might have not given this because this is basically in an example they gave a definition of the buoyant force or the amount of the buoyant force. That is just one example here. And the viscous force is also an example. The air resistance is also an example. And there are also other examples as well, where there is contact forces between solid and which can be liquid, which can be gas as well. Two other common contact forces, or not contact forces, common forces are tension in a string and the force due to the spring. Two other common forces are tension in a string and force due to a string. Let's read that again. Two other common forces are tension in a string and not a spring but a string, and the force due to a spring. When a spring is compressed or extended by an external force, a restoring force is generated. Okay, this force is usually proportional to the compression or elongation, that is for small displacements. The spring force F is written as F equals minus kx, where x is the displacement and k is the force constant. Okay, basically other common forces are spring force here. Spring force is basically when we compress or stretch a string, there is a restoring force developed. This restoring force, the second point, this restoring force is directly proportional to the elongation or compression of the spring, which is measured in terms of distance or displacement. For small displacements, this elongation and compression we measure in terms of displacements, so that is why it is directly proportional to the displacement. They are saying here force is proportional to displacement, where x is displacement, and force is equal to minus k times x. This is the force formula due to a spring, the restoring force of a spring, where k is the spring constant and x is the amount of elongation or compression of a spring, and minus indicates that it is a opposite force, indicates it is acting opposingly from the external force, opposing the external force. Because when we extend a spring, the force will be trying to restore the spring inwards. And basically, let's see the diagram here. If this is a rigid body or rigid support, this is a spring. When we elongate the spring by applying force like this, where the displacement, let's assume this is the displacement of the spring, and in the second case scenario, I mean the restoring force in this case, this is the force external, and the restoring force in this case will obviously act in this direction, which is F restoring. And in case of the second case, where the force is acting, F external is acting in this direction, where this is the displacement here, it got compressed this much, the force, the restoring force will act in this direction, the restoring force. So where in both the cases, where it was like this and here like this, force restoring, and in this case it was, just a minute, Okay, then let's continue. I was talking about the force in the first case where it's an elongation of spring. Elongation of the string also, here also, the force external is opposite of the force restoring, and here as well, the force external is opposite of the force restoring. That is the reason they took a minus sign here. This is the final formula for force of a string. Okay, then let's continue. Oops. Okay, good. Let's read the paragraph again. Two other common forces are tension in a string and the forces due to a spring. Forces due to a spring. And when a spring is compressed or extended by an external force, a restoring force is generated. This force is usually proportional to the compression or elongation of the spring. The spring force is written as F equals minus kx, where x is the displacement and k is the force constant or the spring constant. The negative sign denotes that the force is opposite to the displacement from the unstretched state. For an inextensible string, the force constant is extremely high. The restoring force in a string is called as tension. We came out from the spring topic and we are coming to the string topic. What a complex way of naming things. It's not really complex, but still. The restoring force in a string. Now we are talking about a string here. String, the restoring force in a string. Wait. Here as well, it's a string. For an inextensible string, the force constant is very high. The force constant, okay, basically, for an inextensible string, the force constant is very high. Okay, similar to a spring, actually not similar to a spring. When we take care of us, when we talk about a string here, since for an inextensible string, we cannot even extend it. We cannot increase the displacement. We cannot elongate it, or we cannot compress it. In such a case, we cannot compress a string in actuality. We can only talk about elongation here. When there is in an inextensible string, or in case of a rope, if it's an inextensible rope, we cannot extend it no matter what. So the force constant, or they called it force constant here. So this force constant is very high in case of a string or a rope where it is inextensible rope. The restoring force in similar to a spring here, there is also a restoring force in the string as well, which is a rope. The restoring force in a rope is called tension. It is customary to use a constant tension T throughout the string. Basically, we don't usually take tension in one part of the rope to be separate from different other part of the rope. We take the tension in the rope to be always same throughout the rope. This assumption is only true if the rope is of less mass or negligible mass. Basically here, zero mass. There is always a certain amount of difference in tension in reality, but in case of ideal situation where the rope is massless, the tension is also constant throughout this rope. We learned that there are four fundamental forces in nature. Of these, we know that there are four fundamental forces in nature, and of these forces, the weak and strong forces appear in domains that do not concern us here. Basically, the weakest force is gravitational force in nature, and this force we will study about more in gravitation chapter, which we have in the 11th textbook. And in case of the strongest force, which is a strong nuclear force, and this is also which we are not going to study in our 11th and 12th classes. That's what they mean. These domains of the weak and strong does not concern us here. Only the gravitational and electric forces are relevant in context of mechanics. The different contact forces of mechanics mentioned above fundamentally arise from electrical forces. Basically, sorry for that. Anyways, how these contact forces are generated, these contact forces originate from the electrical forces. How that is because matter is made up of atoms, and atom contains positive base of nucleus and electrons revolving around the nucleus. So in such a case, we know that like repels and unlike attracts. This is in case of magnets. This is in case of magnets as well as electrical charges. Positive charges are repelled by positive charges and attracted by negative charges. So in such a case, these contact forces arise due to the electrostatic interactions or electrical interactions between the bodies, between two bodies. Due to the electrostatic interactions, there arises the contact forces. This is actually kind of obvious, but fine. This may seem surprising, subscribing, since we are talking about uncharged and non-magnetic bodies in mechanics. We are talking about here uncharged and non-magnetic bodies in nature. So how do we have electrostatic repulsions and all? Basically, we know that because atoms contain nucleus, and which is positive, and electrons which are negative. When we take at the microscopic level, all bodies are made up of charged constituents, nuclei and electrons, and that is what I meant there. And the various contact forces are arising due to elasticity of bodies, molecular collisions, and impacts, etc., can ultimately originate to the electrical forces between the charged constituents of different bodies. The detailed microscopic origin of these forces, however, complex and basically not usable for handling problems in mechanics at the macroscopic level. Even if we know the exact constituents of these forces, it is basically completely useless for us in determining problems of our real macroscopic world. Even microscopic world is real, but not in case of the macroscopic world which we live in and which we want things to be done. In such a case, when we want to pull a trolley, we don't think about the electrostatic interactions between the trolley's wheels and the ground. If that is the case, it will take, as there are many millions of atoms, billions of atoms actually, or even trillions, even more. If we individually calculate the electrostatic attractions between them, it will take too much time, and which is basically useless. We just want to pull or push a trolley, and we don't need to do that. And we don't need the electrostatic interactions to do that, to do such a menial task. This is why they are treated as different types of forces with their characteristic properties determined empirically. Okay, this is why they are treated as different type of forces. Okay, basically, since we don't need to calculate such electrostatic constituents for real life problems, that is why even though the contact forces which originate from the electrical forces, we separate mechanics from the electrostatic interactions or electric forces. This is a different chapter we are going to study about in 12th class. Let's see our diagrams. We should not miss the diagrams here. These are some examples of contact forces in mechanics. This is a crane lifting. Here there is a tension in the crane's wires. Basically, a tension, which is this tension and this tension are equal. The force is due to gravitational force. This is a crane, I think, and this is a spring. This is the spring constant force. This is the restoring force on the spring, the force on the spring or by the spring, and this is the gravitational force. and this is when we steer a bucket. This is also contact forces. This is also contact force. Okay. Next, let's go to the next main topic, which is, wait, yeah, it is under the common forces, which is basically friction. A very, very common term which even layman know is friction. Let us return to the example of a body weight. Let us return to the example of a body of mass m at on a horizontal table. This is a diagram here. This body of mass m on a table. Okay, the normal force, not normal, the force of gravity m times g, which is m is the mass of the body and g is the acceleration due to gravity, is cancelled by the normal reaction force n of the table. This is what we studied before. And now suppose a force of F is applied horizontally to the body. What they mean is, this is basically the body, we are applying force like this. Like this. That is what they're saying here. We are applying a force like that. We know from experience that a small force applied may not be enough to move the body. Basically, if you think that is the case, try pushing a rested truck. Don't actually try it, because we know that it is not possible for a human to push a truck. And we know from experience that a small force applied, that is basically what they're saying here. We know that experience that a small applied force may not be enough to move the body. Okay, that is okay. But if the applied force F were the only external force on the body, okay, let's assume a scenario. This force is the only external force on the body, then it must move with an acceleration, force per meter, however small. No matter how small the force is, if there is no other external force acting on the body, if there is no other external force acting on the body, only this force which are applying here, the external force, only this force here, only this force is acting. Let's assume that is the case. If that is the case, then no matter how small the acceleration, when force is applied and how high the mass of the body, there should be some acceleration on this body. That should be the case. But however, clearly the body, but we know that clearly the body remains at rest because of some other force come into play in the horizontal direction and opposes the forces, the applied force F. Okay, we know that when force is applied, a body should move if there is no other external force acting on it. But we know that the body is not moving. Then how is the body not moving? It can only not move when an external force is resisting that movement. And this resisting force is the frictional force. Let's read the statement again. Body remains at rest because some other force comes into play in the horizontal direction and opposes the applied force, resulting in zero net force on the body. The contact force F static, parallel to the surface of the body in contact with the table, is known as frictional force or simply friction. Basically, this Fs here, which is F static frictional force, which is static friction, which is parallel to the surface of the body in contact with the table, is known as the frictional force or the simple friction. This subscript for the subscript stands for, basically the subscript is the subscript of S. This stands for static friction to distinguish between kinetic friction. There are two types of friction here, that is static and kinetic, that we consider later. Note that the static friction does not exist by itself. But before that, let's see the diagram. Static and sliding friction. A, this is the static friction diagram. Impending motion of the body is opposed by static friction. Impending meaning like the about to come motion of the body. It's not moving, it's in the rest state. When it's in rest, the body is in rest. When we apply force, when we apply a large enough force, the body should start moving. And this moving is opposed by a static friction. At the start, when we are moving a body from rest to like some kind of acceleration or velocity, this is opposed by opposing force, a friction. This is called as static friction. When external force exceeds the maximum limit of static friction, the body begins to move. But still, when the external force exceeds the maximum limit, the maximum amount of static friction there is, the body will start to move. Let's see the kinetic one now itself as well. Once the body is in motion, it is subject to sliding or kinetic friction, which opposes a relative motion between the two surfaces in contact. Kinetic friction is usually less than maximum value of static friction. Basically, once the body is in motion, it will subject to sliding. It is called a sliding motion. This sliding motion or kinetic friction, which this kinetic friction opposes this motion, this sliding motion. Friction is itself is an opposing force, so it will oppose the sliding motion of the body, which opposes relative motion between the two surfaces in contact. Kinetic friction is usually, and they are giving property here, normally generalized case, friction kinetic is less than friction static. That is why when we initially start to move a body from rest, when we are pushing a block from rest, at the start it is a little harder to start get the body moving. But after it is moving, when we are pushing it, when the body is in motion, the force applied is little less than the starting force. That is the reason, because the force of friction kinetic is less than friction static. And note that static friction does not exist by itself. This is the point to be remembered. When there is no applied force, there is no static friction. If there is no applied force, there is no static friction itself. So that means static friction will only exist if there is an applied force. It is dependent on the applied force. It comes into play the moment there is an applied force. As the applied force increases, static frictional force also increases, remaining equal and opposite to the applied force up to a certain limit. If it was all the time, it was actually opposing the the frictional force, not frictional force, the applied force. If the static frictional force, it was opposing the force for with no limit itself, then the body will not move only, it will just stay there. But we know that the body will move, so that we can say the static frictional force only is possible only after a certain amount of time. Keeping a body at rest, remaining equal and opposite to applied force, and thus keeping the body at rest. Hence, it is called as static friction. Static friction opposes the impending motion, the motion that is about to come, the moving of the body that is about to happen. That term impending motion means motion that would take place but does not actually take place. It didn't basically this it is more specific to tell it didn't actually takes place, or does not actually okay, fine, didn't actually takes place, did not actually takes place under the applied force if friction were absent. We know from experience that as the applied force exceeds a certain limit, the body begins to move. It is found experimentally that the limiting value of static friction, Fs maximum, is independent of the area of contact and varies with normal force N. Basically, this value of the static friction, which is maximum value of static friction that the due to the contact with surfaces may provide, it is independent of the area of contact. No matter if it is a box of 20 box, two boxes, let's take, if 20 meter, and if having two boxes made of same material, if we take one is having an area of 20 meter square in contact with the ground, and another box having an area of 100 meter square in contact with the ground, in both these cases, if the weight or the if the mass of the both the boxes is same, then the maximum friction obtained, or maximum static friction value, is also will also be same for both of them. It is only depend on the normal force. It only depends on the normal force of the body. We cannot say weight because they are talking about, why not say the gravitational force? Why not say it is the gravitational force acting on the body instead of the normal force, and keep a negative sign there or something like that? Why not? That is why they did not take gravitational force here, is because what if you are standing on that box? Then what? Then should we add the gravitational force of both of us, of both of the me, or if the person standing of the box and the weight of the box? That can also be correct. But if they did not mention the force, if they did not mention the, if they just say we are putting a force on the board like the box, then we add up the gravitational and the force that is applied. But it is simpler to say normal force instead of that. That is the reason, instead of putting gravitational force Fg, they kept normal force. No matter how much the force, the normal force will be exact opposite of that and equal to that. So it is better to say normal here, normal force here, where mu s, where frictional force maximum is maximum frictional force that is possible, which is equal to, which doesn't depend on area, and it varies only with normal force, and it is equal to the product of normal force times mu s, where mu s is the constant of proportionality depending only on the nature of surfaces in contact. We know that the friction in case of ice and a normal rough tar road will be different. That is what they mean by nature of surfaces. The difference between a tar road and tails we can take, or even ice block, it will be different. The constant mu s is called the coefficient of static friction. This mu s is the constant of proportionality, and it is the coefficient of static friction. The law of static friction may be thus written as, the static friction may be equal to or less than the static friction times normal force. Normal force. If it is equal, the body will, if the static friction is equal to or more than the force applied, then the body will remain in motion. But if the static friction is less than the force applied, then the body will begin to move. If the applied force exceeds the Fs max, the body begins to slide on the surface. It is found experimentally. Why we take it as a less than mu s times n is because it, if it is only equal when we take frictional maximum static frictional force that is possible. That is why we take, normally the static friction may be less also than this value. This value, this mu s times n, is only for the maximum static friction value possible. And it can also be like the normal static friction can be less than, also less than mu s times n as well. If applied force exceeds Fs max, the body begins to slide on the surface. It is found experimentally that when the relative motion has started, the frictional force decreases from the static maximum value. Basically, they're saying if the applied force F, which is the external force, that is exceeding the frictional force, then the body will begin to slide on the surface. And it is experimentally found that when relative motion has started, basically when the body started moving, then the frictional force decreases from static friction maximum value. That is what here we saw that static friction, wait, here they gave the kinetic friction is less than the static friction. That is why we know that the friction value will decrease from the maximum static friction. Frictional force that opposes relative motion between surfaces in contact is called as kinetic or static friction, and it is denoted by Fk. Kinetic friction, like static friction, is found to be independent of the area of contact. Further, it is nearly independent of velocity. It satisfies a law similar to that for static friction, where it depends on the normal force, normal reaction, where Fk equals mu k times n, where mu k is the norm coefficient of kinetic friction. And points to be remembered in both kinds of friction is that the frictional force is independent of the area of the contact surfaces. A point to be remembered, very, very important, that it is independent of the areas in contact. And it only depends on the, we can say, the nature of the surfaces in contact and the normal force acting on the body, or normal force experienced by the body, where mu k is the coefficient of kinetic friction, depends only on the surfaces in contact. As mentioned above, experiments show that mu k is less than mu s when relative motion has begun. The acceleration of the body, according to the second law, is F minus mu k by m for a body moving with constant velocity. Basically, they gave two information here. The first information is, we know that static friction is more than kinetic friction. So coefficient of static friction is also greater than coefficient of kinetic friction. That is the first information. When a relative motion has begun, when the body has begun moving, then the acceleration of the body, according to the second law, basically the second law is force equals mass into acceleration, where acceleration equals force per mass. And when we know, in case of a rough surface where there is a friction involved, the acceleration of the body will be equal to F minus Fk. This is in case of motion, when the body is in motion. This is the total force. The net force acting on the body is F minus F friction, kinetic friction, by mass of the body. And for a body moving with constant velocity, if the body is moving with constant velocity, where force equals Fk, friction is equal to force, frictional force is equal to the applied force. If the applied force on the body is removed, its acceleration is minus Fk by m, and it eventually comes to a stop. Basically, they gave two more information above the first two information. The third information is basically when, okay, let's write it separately here. Frictional force, which is equal to F, let's denote it with small f, Fs equals mu s times n, Fk equals mu k times n. And in case of the first case, first information is Fs is greater than Fk, and second information, okay, first information is about the nature of the surfaces. It only depends on the nature of the surfaces in contact, and also the normal force. And when a body is moving in a rough surface, on a rough surface, rough surface, meaning friction is involved. It started moving, it's already moving. Then acceleration of the body is acceleration equals F minus F of K by M based on a force equals M mass into acceleration. And third information is when the force on a moving body suddenly is removed or is removed suddenly, then the acceleration of the body is minus Fk by mass of the body. This is obvious because the only during this scenario, the only force acting on the body is Fk, and it is minus because it is retardation, not acceleration. It is reducing or deceleration. And it is an opposing force. That is basically the information they gave. And eventually, after some time, it will come to a stop. And as for how much time it will go, if they give the initial velocity of the body, and if they give the frictional force or the friction kinetic constant, basically coefficient of kinetic friction, mass of the body, we can calculate the distance it will travel, the time taken as well. The laws of friction give above do not have the status of fundamental laws like those for gravitational, electric, and magnetic forces. Basically, these laws of friction, they do not have the status of fundamental. This friction is just a part force, like it's not completely. We do not have fundamental laws. This is not a fundamental force. Friction is a very important force, but it is not a fundamental. It does not have fundamental laws like those for like gravitational, electrical, and magnetic forces, and they are empirical relations that are only approximately true. Whatever we calculated here are only approximately true, but they are very useful in practical calculation in mechanics. They are very useful in our real life, in our real situations. That is the reason we are studying this chapter. Thus, when two bodies are in contact, each experiences a contact force by the other. This is basically the third law. Third law, Newton's third law. When two bodies are in contact, each experiences a contact force by the other. And this contact force is equal and opposite. Friction by definition is the component of the contact force parallel to the surfaces in contact, which opposes, let's continue reading and I'll repeat it again, impending or actual relative motion between the two surfaces. Basically, friction is the component of contact force that is parallel to the surfaces, where theta is 0, the angle between the force, the direction is 0, and this force opposes the impending motion in case of static friction, and the a relative motion in case of the kinetic friction between the two surfaces. Note that it is not motion but a relative motion that friction poses. Basically, it's a very important to remember this kind of minor things. It is important to remember that the friction opposes not motion of the body but relative motion of the body. As how that, what is that meaning? What that means is, basically, mm, let's consider two cases. First case, when there is two blocks on each other, one rough block like this, and there is one more block like this. They are in contact here. They are in contact. Let's make this rough block a little longer, and this block is moving. In this case, only this I mean, that became a triangle, but that is not a triangle. This is A, and this whole thing is B. When it is moving, in this case, when it is moving forward due to a force F, there is a force in this direction, which is basically Fk or Fs if it's in rest. Basically, just some frictional force acting on it. This is F friction force, frictional acting this side. This is what they mean by relative motion. Relative motion. Relative motion meaning with respect to B, A is moving. With respect to B, A, the body with respect to body B, the body or block A is in motion, is called as a relative motion or movement. But in the second case, let's assume the second case, the same two blocks, block A and same block P. Let's take this is the case. This is the case. Now let's assume we take this whole two blocks up in the air, or let's assume these blocks are on Earth. These are on Earth. These are somewhere situated on the globe. The globe should be blue in color. The oceans. This is the Earth, which is slightly tilted. This is the axis of the Earth. Let's assume this is the axis of the Earth, and wait. We don't need an axis here, and this Earth is rotating around the sun. So we can say everything on the planet is moving. Everything on the planet as Earth is moving, and we can also say Earth is rotating like this on the axis, rotating like this. There are two motions Earth is performing, that is rotational motion, and there is also it is revolving around the sun. So we can say everything on the Earth is also moving, and these two blocks which are on Earth are also moving. So does that mean there is a frictional force here? There is no friction. A with respect to B, if A is moving, then A will experience a frictional force. But that is not the case. Earth is rotating here. With respect to Earth, there is no frictional force here if A is not moving or B is not moving here. That is what they mean by relative motion. Only with respect to block B, if A is moving, there will be a contact force, which is friction, that will oppose the motion, relative motion of A. I will be taking a 5-minute break. It take too much times. It takes too much time for explanation, but fine. 5-minute break. Let's change that 5-minute to a 20-minute break because it is my dinner time. 20-minute break.